doing screen mirroring? Nope. What did I do? Yep. Are we good? Good? Okay, all right. Morning, everyone. How are you guys doing? Good? Okay. So day 9, right? One more day to go. Have you guys learned something so far? Yes. Okay, good. So what we are going to do, I'm not asking the questions where did we leave yesterday, because today we are going to do applications, right? And as I mentioned that I'll pick 2 examples that some of you had suggested or asked for or showed that that's the area in which you're interested or you're working. So we're going to do that. So overall, 3 different use cases that I'll pick up or examples. Majority of them, 2 of them are 2 application domains. So you're going to see how exactly whatever we have learned in the last 8 days, you'll see a lot of common terms. You'll see how exactly you map those into problem areas. So 2 of them are studies, literally in a way, published work that describes the project or work that was done. Should be easy to replicate, because both the papers I picked up were such that if you want to test them out, you should be able to test them out as well. Third one is because a couple of you had interest in figuring out if I want to design the LLM, how exactly we're going to do. So I'm going to go over the steps and processes. There are a couple of different frameworks that you can use which provide you building blocks so that you don't have to really start from very scratch, i.e. You don't need to really build a neuron first or a perceptron first or implement the backpropagation algorithm or feed forward. All of it is now available as part of libraries and frameworks, so it's not that difficult to experiment with building some kind of a language model or a network, right? So we will talk about that towards the end. Okay. So we'll look at some applications, key technologies, in a way that whatever we have done or learned so far in the last 8 days, we'll continue to focus on that. So first example I'm going to take would be if you are going to build a chatbot or a dialogue system. So how exactly you go about it. Now, the reason I'm using this is this predates the neural networks. Theoretically speaking, you can build a chatbot or a dialogue system without ever using a neural network system. As a matter of fact, very first example of AI, and I refer to that, the name ELIZA system, was written without having any idea of how neural networks work, what's deep neural network, etc., right? The idea there was that it has to pass the Turing test. We talked about Turing test, I think either on the day 1 itself or maybe on day 2. Right? So you could write a chatbot without ever really implementing or considering the neural networks at all. So we're going to look into the 2 different ways of building the chatbots. I am skipping the math part, but you know the basic math basically, but we'll see how you take a problem, map it to the tools or techniques that you know, and then figure out the solution. Right? So that's what we're going to look into it. Let me just say this, any questions at this point of time from the areas that we covered yesterday, because today we're not going to talk about any of those, but you can think about some of them as we look at each applications, right? So if anybody has any questions from yesterday. No? Okay. All right, let's start with a chatbot or a dialogue system. Is there anyone who has never interacted with a chatbot or some kind of a dialogue system? Right, so all of you have, right? Do you have a preferred one or one that you like? Or the other way, something that you did not like? Okay, let me make it easier. Can someone tell me which specific dialogue system or a chatbot have you recently interacted with? Sorry? Alexa. Is that what you said? Okay, anybody else? Yep. Eliza B. Where did you find it? Okay. I mean, see, you call a bank, for example. Let's say you have an account in ICICI Bank, right? You make a call. I'll tell you why I'm taking this example, because yesterday I was with someone. They had to make a call, right? It never goes to a human directly. It goes to a chatbot, roughly. Any idea how that chatbot is working? If you have ever encountered this, how exactly it goes? I think first it asks you to pick your language. At least the ICICI one did, right? Then it says that, do you want to do a checking account, saving account, whatnot, open a new account, etc., right? Then you pick an option, then it goes few more questions, then it goes a few more questions, etc. And finally, either you get it answered or say resolved, or it says that go back. And there's a third stage as well. Any idea what the third stage is? Frustration. Because what happens is that you wanted to get something done, you spend like 5 minutes following all the options, and eventually discover that that's not what you wanted. Or it says that you cannot do what you're looking for doing it, right? How does that work? This is called a call tree, if you have heard that term, right? No different from the search tree, but what is happening is that you as a user have no choice. I mean, fine, you are given an impression that you have a choice because at each level you are picking an option, but even if you know fully well what you want to do, which in this instance last evening, we knew what we were trying to do, but we couldn't get through the person. And eventually what happened is that trying to get it done online or through the phone system or through the chatbot resulted in actually visiting a branch because we couldn't get it done. The people in branch couldn't get it done. They had to somehow figure out how to get it done. Point I'm trying to make is that chatbot old way had a fixed logic. If your requirement doesn't fit in here, chatbot is of no use, right? So some examples that you may have seen, Siri, Alexa, Cortana. Cortana was one of the Microsoft's chatbot, Google Assistant. They can do a lot of things. They can play music for you. You can just give them instructions and they'll respond to it. You can chat with them for fun. Eliza, when it started, people actually find it very addictive in the sense that it can chat with you forever, actually. I mean, I wouldn't say forever because you do reach this stage. Think of it this way. Any chatbot which is using a fixed kind of a tree mechanism to navigate, eventually you will end up at that stage where you'll say that, okay, it's not making sense. So, but that's a couple of places that you are. Booking travel reservations, usually you will see that the travel reservations, you are dealing with a chatbot. I'll ask you a few questions. Majority of the time, maybe it will successfully make a reservations, maybe not. It is being used for mental health. It is being used to figuring out people who are feeling boredom, more so in the Western countries where there are not enough people available, but increasingly, I assume, in India also. If you are alone, if you want to find someone to chat with, the chatbots are being used to help with not necessarily mental patients, but mental health related issues. Right? So there are two distinct type of conversational agents that you can think about it. One is mimicking human chatting for fun, for therapy, or for maybe doing small tasks. The other one are dialogue agents specifically just doing the task-based systems. Right? Say for example, on phone, Actually, phone, I would say both ways. Siri primarily is a dialogue agent for chat, for the task-based. If any of you have used Siri, you might ask it, okay, set me an alarm for 6 a.m. next morning, right? Find out or play music or find a file on my phone or call this person. It will do that task. Generally, they are interfaces. So what is happening is that they're not necessarily doing the task. They're basically initiating the task on your behalf. So if you make a call, hey Siri, I mean whatever is the call word, and then say do this, it's only initiating that functionality. That app should exist on your phone. So they are acting as an interface. They're usually available in appliances, they're robots and cars, all kinds of things have now a voice enabled access, so a layer on top of the actual functionality. Flights, booking, restaurant, things like that. Right? Two different kinds of conversational agent. As I said, one is purely a chatbot with some functionality for task, and the other one is only specifically related to task. Now look at it, how exactly you design them. One is based on the rule base, which is really the rule tree or a call tree. The other one is corpus based. Now what does that mean? That there is a database of actions and responses. It is not necessarily already structured like a tree, but you have it somehow. And anytime when you are trying to have a communication, it's searching through it. It's retrieving the information, or the last option, neural encoder decoder, which is really using neural network to build a chatbot. Does that make sense? Right? Any system that you're building requires some data. You can call it data, information, knowledge, whatever it is. It needs to be organized in some way, shape, or form. Why does it need to be organized? It needs to be organized because it can be searched easily. If you organized it as a tree, the search path is predefined, right? If you organize it in some other way, search could be more generic, right? On the other hand, if you are going with a neural encoder decoder network, your hope is that the bot can do more than what it is explicitly being told. Same thing that we discussed earlier, that there is a latent space, it discovers information on its own, it can answer the questions even if it has not seen that question before. That's the whole idea, right? So if we continue on that topic, the task-based or goal-based dialogue agent, where you do have a well-defined task, whether it's setting a timer, making a travel reservation, play a song, buy a product, any of those kind of things, make a phone call, which is not there yet. These are called task-based or goal-based system. Now, why they are differently defined? Because it's very straightforward way. Like you need to make a phone call. All that the agent need to do is to search in your contacts that person's name, find out the phone number, and then initiate the call using whatever the phone app you have on your device, right? Their architectures are usually very straightforward because the goal is defined. The intermediate step that you need to take to reach to that goal is defined. All it needs to do is to fill some information or some gaps. Either it can do it on its own, or it will ask you the question to provide this information. So say for example, I'm trying to make a travel reservation and I say, hey Siri, can you book me a ticket for Delhi? Maybe it will say, yeah, sure. Now it will go to a goal-based system and it will say that, okay, I know the person wants to book a ticket for Delhi. Now it will say that, do you want a train ticket or a plane ticket? Because it will see that one of the frame or task needed is to figure out what ticket. Then it will probably ask for which date. Then it will probably ask for, do you have a preferred airline or something of that nature, right? So that's the task-based or goal-based dialogue agents, theoretically speaking, because you know what is needed to achieve that, you're trying to get that information. So it will look something like this. The frame is the structure or the organization that's called, in the sense that this is the information you need before this task can be completed. Think of it this way. That's a frame for train reservation. If you're trying to make, let's say, purchase a product, or if you're trying to make a phone call or arrange a meeting, book or get a restaurant reservation, the frame may look different. Is that point clear? Right? So basically what you're saying is that you're building a dialogue system which basically has a goal. You could have a dialogue system which can only support one goal, or it may have that it supports like 20 different type of goals. For each of those goals, you define what is the basic information that's needed to be filled. And then the intelligence of the dialogue agent comes in is that how many of these pieces for that specific task can it automatically fill. That could be based on your information that you've already provided, like your contact details. If it says that call my dad, if you have already labeled a contact as dad, it already knows that. It already has the phone number. If you ask it to make a phone call to Barack Obama and Barack Obama is not in your friend list or not in your contact, it'll probably ask the question, what's the phone number for Barack Obama, right? Same way, if you're trying to make a reservation, it says that it needs to know which city you're starting, which city you're going to, what's your departure date, what time, what's your preferred airline, etc., etc. If you have already provided defaults or have a profile set up, it will fill in all this information for you automatically. If not, it will ask you a question, right? Not that very difficult. As a matter of fact, it should be a couple of hundred lines of code and you should be able to write a chatbot agent provided for simple works. Sending an email, sending out a chat, making a phone call, all of those chatbots things can be prepared using some kind of a goal-based or a task-based model, right? Now, let's say you want to extend this to a slightly different way of communication. There are two different possibilities here. If you think about it, how many of you have used any travel websites? Which one have you used? Make My Trip, right? Make My Trip would probably have a form. That's a usual interface when you're trying to get something done, is that you basically have create a form. So that's one way. You can actually say, I don't need to create a conversational agent. I will just create a form. You just type in what you want, click the button, submit, reserve, book, whatever it is called, and then it'll be done. Behind the scene, it might run some validation. It might see that, okay, you can't be leaving on a date that has already passed. So I'm saying book me a ticket for January 5th, 2025. So there may be a validation saying that, hey, January 5th is already gone. You can't book a ticket for that. Or you can't say that your origination and destination locations are exactly the same. You probably don't need a ticket then, right? So all of this can happen. But in some cases, the company might say that people, they don't want to give a form as an interface, so it could be a conversational interface. It could be something like this. Not exactly the example of the travel booking, but a conversational agent. Now, if you read through this, let's say, what does it feel like? Does it look like that it has a goal-based implementation, or is it somewhat different? This comes from, again, a published work. I have a reference there, I think 1966. Yes, that's what I was saying. It's 1966, 1960. So somebody else who mentioned ELIZA is probably a variant of this, which is probably available. If you search around, you would find modern implementation for this kind of a conversational agent. These agents, written in a very simple way, can actually keep you engaged for a long time. Now, long time might be few minutes, maybe tens of minutes, but because they're all using some kind of a defined methodology, you will end up in this state at some point of time. It will end up asking same question over and over again, or it will get into a loop of 4 or 5 questions where you answer and it doesn't matter what you answer, it keep on asking the same set of 4 or 5 questions. That happens. But anyway, what does it look like? Do you think it is using some kind of a frame structure that I showed earlier, or is it doing something different? Do you realize what kind of technique is this conversational agent employing. Or let me put it this way, if you had to design something like this, how would it go about? How would you go about it? What is it doing? Have a look at it and see what exactly it's doing, or at least make some kind of a educated guess. So if you notice, there are 2 or 3 techniques it's using. You can call it heuristic also, you can call it design elements also. One thing it seems to be doing is that it has some trigger words. So if you say that trigger word, it knows which question to ask after that. If it cannot find a trigger word, it will ask you to define what do you mean by that. If it cannot do any of that kind of thing, right, it will ask the question turned back. You're not very aggressive, but I think you don't want me to notice that. What makes you think I'm not aggressive? Now, that's a pretty stupid question to ask if you want. If you ask me that, it says you're not aggressive, great, that's like a positive thing, but it says, oh, because there's no intelligence here, right? It's either trying to find a trigger word that it knows about so that it can ask the next question, or ask you to define, or just simply ask a counter question. You say that you're great. Oh, what makes you think I'm great? Or what makes you think that I'm not great? Or whatever the question. So that's what it's doing. Now, this is a specific style. If any of you have studied anything in psychology or clinical psychology, there's a specific way of training that psychologists have called Rogerian psychologists, because the work of the psychologist is to understand your thought process. And the way they do it is by asking questions. They do not have, okay, I shouldn't say that they do not have a prescribed set of questions. They have a prescribed set of input that they want from you. But they do not want this to be a monologue, like they ask 5 questions, you give 5 answers. They want to dig deeper. And the way they do it is exactly what Eliza is doing, in the sense that they will take a clue from your answer and then quiz you more about that. Why did you say that? Why did you do that? Why did you not do that? Etc., etc. So what it is doing, the ELIZA, which is right from 1966, that's exactly what they did. So another thing, I would mention it one more time here, because I have an opportunity to do so. If you are doing your research, if you're trying to do something else, look around, see what other fields are doing. So in 1966, somebody wanted to create an intelligent conversational agent. While trying to figure out what's the best way to do it, which is not like a call tree, they thought, why don't we model it like a psychologist? And on that, specifically a Rogerian psychologist. What they do is that they play the patient statement back at them. Sometimes they will exactly repeat the same statement because they couldn't figure out what the next question. They'll repeat the same thing, hoping that the patient is going to say something more, right? That's the style. You can say that I know nothing about the real world. I'm only going to ask you whatever you say. Let's say the patient says that, so let me give you 2 examples here, because I wanted to say, somebody might say that, I hate traveling by air. Now, hate is a trigger word in the sense, but immediately they'll ask the question, why do you hate air travel? Right? So basically you're saying that you know nothing about. If, let's say, somebody is coming from Sangam area here, and the person says that, oh, it took so long to come. Why did it take you so long? Oh, there was traffic. Why was there traffic? Is it unusual to have a traffic? Right? So they assume the pose of knowing nothing. The advantage of doing that is you don't need intelligence. Really, you don't need intelligence because you're claiming to know nothing. You're asking questions, gathering information. That's how a lot of earlier chatbots which claim to have passed Turing test, and they did. Because if you think about it, the Turing test was if a person is interacting with a human and a machine, if they cannot figure out who the human is, who the machine is. Now, what happens, as I said that, these kind of systems can play this game for a little while. And if the person is smart, they'll very quickly figure out that this person is just getting into a loop, because you do end up in this kind of a stage very quickly. Now, very quickly might be few minutes, maybe half an hour for someone, maybe half an hour for some very good implementation of a Rogerian psychologist, right? But eventually you will get to that point. Some of them are really good. I mean, in the sense that they know how to continue the conversation. I went for a long boat ride. Now, I didn't know what to ask for. I said, okay, tell me more about boats. What kind of boat was it? I mean, there are very good implementations which can keep someone communicating for hours. Now, keep in mind, these are systems for people who are either fighting with something. That something could be loneliness, or something could be a mental situation. These people may be okay with very limited vocabulary, with actually getting an opportunity to speak for hours might work, right? So again, I'm trying to explain here is that what is Rogerian psychologist is, but you can definitely try to build chatbots depending on your use case, and these bots using this methodology will work. Okay, so we saw two ways of implementing chatbots. One using something called a tree structure, one using a technique called assuming a persona of a Rogerian psychologist and then playing the prompt back to the user and drawing them into longer and longer conversation. Apply some heuristics, as I mentioned, a few trigger words. If you don't find a triggered word, ask what it is, like, okay, what do you mean by boat? Tell me more about boat. Or just simply playing it back to the users, hoping that they will give you more information. What else can you think of building a chatbot? What were the two types I mentioned earlier? So these two were based on this kind of structure, like question or playing it back, having some predefined thing. The other one I said is that you have a corpus-based approach, which basically means that you start with some known information, data, or knowledge, right? How do you build a conversational agent or a chatbot using some data that's available to you? So think of it this way. You are trying to interact with a help desk. A help desk, let's say you bought a new computer, or somebody bought a new computer, or let's say a music system. And you're trying to set up the music system and you're running into a problem and there's a help number and you call the help number. Now, that help number cannot play this game because you're saying that don't ask me the questions because I have a problem I want to solve. So all of these help desk kind of systems start with some already known problems and answers to them and things like what they have seen, commonly known as FAQs, right? Frequently asked questions. So if you are trying to build a system which is slightly more intelligent than these kind of bots, you start with some information or some knowledge. The question is that how do you use this to have a better experience for your user? What do you think might be the way to do it? Any idea? Just guess. I mean, come on, we have been talking about a lot of these things from the last 8 days. If you were to build a system, a chatbot, which is supposed to answer questions for, pick whatever, maybe a wall clock, a projector system. It's already failed 3 times, right? So suppose you have to ask someone, you call the help desk, a computer or a modem, for example. I mean, usual thing people find issues with. How would you go about doing it? Come on, something. If I'm running a business, the first thing I'll say that, okay, I'll send a technician home. It'll cost you 500 rupees for someone to show up. They will either fix it or tell you what the problem is and you have to pay more, right? That's one model. A lot of places you call, They don't have any system, but you're simply saying that bhaiya kisi ko bhejo, send someone to get it up and running, right? That's one way of it. But if you're trying to automate that process, so there are two different ways. The traditional way, response by retrieval, I mentioned this. You create a database and somehow search through this database and then say how exactly you could solve this problem, right? How many of you have worked on a Unix operating system? Any idea? Sorry, Linux? Yeah, which is fine. How many of you? Can you raise hands? Not many? Oh, okay. The reason I'm asking for this is, so in my earlier days, I think it must be 1990, I believe, actually, or maybe 89. So I created this kind of a conversational agent. So Unix or Linux, for those you do not know, works on lot of these commands like ls, like wc, like grep. And what you can do, and then an interface to talk to Linux is called shell. There are multiple kind of shell, but original shell was called just shell. And then you can use these commands in a scripting language. Okay? There is also something called man, which basically has a manual entry, right? So manual entry is like your database. Then you have some of these commands. These commands can be combined together to write a script. Okay? So the problem at that time was, and I'm actually surprised that not many of you have seen Unix here. Unix was just coming up, 88, 89. And it was coming up on the mini computers or microprocessors or microcomputers as well. Not many people, even though they were in computers, were aware of Unix for two reasons. PCs were not very popular, so they were not even aware of the DOS. But if they had a DOS, they had a more like a graphical interface. The Unix did not have a graphical interface. It was a command line prompt. If any of you have seen, it was a prompt like this. Right? And you had a command like pwd, which says print working directory, cds to change directory, etc., etc. There were like a couple of hundred different commands, and each command was a standalone program which can be combined in a script form. So very early, as I said, that probably 89, 2 years in my job, I said, okay, I'm going to make it slightly better for the people who do not know Unix, for example. Now, so what I could have done this, which is really the hard coded way, or because I already had this corpus of information, which is the manual pages or man. So what I thought is that, can I use that and then basically add something more? If you want to add more than to what is already provided by Unix as manual, so I said that manual pages were also in some directory, and as you said, you have your own directory, and each file there can be answer to another question. So basically, these files become your corpus or part of the data that you have. Now, what happens is, let someone ask the question, and I follow the same way, trigger word. I pick up the trigger word, but rather than playing it back, I would grep for that word in either the manual space, which is the provided by Unix itself, or your personal, let's call it personal manual. So grep is, oh, okay, let me define the grep. How many of you have used or know what the grep functionality is? So grep basically does, if you say grep, let's say AI in my current directory. So the grep is a utility or a command which will search for whatever is provided here in every file in this directory. So think what is happening. I find a trigger word, I search for a file which contains that word, show you the content of those files saying that this is what you were looking for. So somewhat easy, very rudimentary, almost 35 years ago, some kind of a conversational system, right? Unix manuals were like thousands of pages. You're not looking for it, trying to find out. It was easy if you can search in the index, but if you're just looking for something which is not an index, it was very difficult. You got to read through all of it. So this system worked. Well, pretty powerful because it was doing the search part, which was being done here. It was conversational. You ask a question and I search through it and then tell you that here are 2 pages or 2 files that you should go through. Was it answering the question 100%? No. It was helping in locating that information. That's response by retrieval. So what's going on is it's trying to get the context, which is a trigger word, which is what I was doing there earlier. Searching that information, grab a response, and the command in Unix is called grep. Doesn't matter. You don't need to do this. You can do more fancy things. When I say more fancy things, it would be something like you may have a proper database. You may write SQL queries. You may write NoSQL database and make even more interesting or more complex queries. You may use fuzzy logic, which means that it's not just that word, because the grep is actually searching for exact word. How many of you are familiar with regular expression? Has anyone heard the term called regular expression? Regex, yeah. Come on, anyone who's doing data science should know regular expression. Right. So regular expression lets you define. So let's say I am saying hotel. So I'm not sure should I have H lowercase or H uppercase. So instead of saying that, making 2 searches, I can say that one word, lower or uppercase, with this, right? And this is in the beginning. Or you could say in the beginning H and anything after that. So regular expression is a way of specifying in a fuzzy way what you are looking for. And then there are regular expression evaluators which will actually match with whatever is in there. Regular expression is a very powerful thing. If any of you, and I thought somehow some of you mentioned you are interested in data science. If you are in data science, the regular expressions are a very, very powerful tool that you should be aware of or probably make use of it. Anyway, so that's the response by retrieval, which is how a lot of chatbots were operating in the, let's call it, second generation of conversational agents. How about the next one here? Response by generation. The moment you see the term generation, that sounds like generative AI maybe, right? So what is going on is that modern corpse-based chatbots are data intensive. You might be looking at the case laws, you might be looking at the legal cases, you might be looking at the medical history cases, right? They are requiring to search through thousands, millions, billions of words. So this kind of rudimentary thing where I was supporting about 200 odd pages here, maybe a few hundred more of your personal written thing, is nothing in front of like when you're searching millions and billions of words. There you could obviously do response by retrieval, it will work. But if you want to use the or utilize or get benefited out of the all the new things that have happened in the area of neural networks, you may want to use the response by generation. So now apply what we learned in the last 8 days, and can someone tell me how exactly will this work? You have a lot of information that's available to you, millions or billions of words, which is really the data that you are or you can rely on. But rather than doing response by retrieval, you want to do the response by generation, means use the, let's say, neural network or generative AI to help you here. Come on, any idea? Any to play Tombola, the one who has not crossed any square yet. So if you haven't spoken so far in the last 8 days, you should speak up now, right? See what we are doing. I mean, if you're doing response by retrieval, you're trying to search through whatever information is available to you. If you're doing it by generation, what did we do in generation? We said it yesterday, right? If you're trying to build the AI system, what do you do first? What's the first step? Rather than building the database, you actually train. You train the model. You train the model in whatever information is available to you. And then predict the next word. Given some context to you, you predict the next word. And while doing that, you generate the answer. So it will look exactly the same what we have been talking about last 3-4 days. User gives you a term or a query, and whenever the user's turn is, and you have the lot of this data, let's call it C, which is a corpus of conversation. What you're trying to do is to find out an R, a next term or a sentence, which is very similar to Q. That's what you're doing. Here I use the grep command to do it. Now you are saying that I don't know. I learned everything that was in here. When I say learn, it has been converted into a high dimensional vector space. I form the vector of the user's question or user's query and then say, can I use that to find the most similar thing in my database? Right? One other thing I mentioned earlier in the sense that you're doing a vector dot product to find out similarity, right? That's what we were doing earlier in the attention mechanism, which we were talking 2 days ago. So exactly the same thing is happening here. The only thing I added here is that I mentioned that what exactly is going on there. It's called TF-IDF cosine. You can search for it, especially those of you who have interest in it. It's called term frequency and inverse document frequency. Very similar to how the Google search functions. Does anyone know how Google search functions? So 2 things. First of all, the Google search is not using generative AI. It is still doing the first method which I mentioned, which was the response by retrieval. What it is doing, but it is employing something very similar to TF-IDF cosine calculation. It's not doing the calculation at the runtime. Basically, what it is doing is, okay, a computer science question. How many of you are familiar with indices or trees? Okay, which one? What do you know? B tree? You're familiar with that. Okay. How about the inverse list? Have you ever heard of inverse list? No, not inverse. The index which is in the reverse indexing. Any idea? Okay. I'm not familiar with B tree. B tree, anyone know? Okay, let's not go there then that far. Basically, what is going on here is, let's say you are using Google search. Google has, let's say, I'm taking a very simple example, only access to 100 documents. Let's say it's a day 1 when the Google search was invented, right? What is Google search doing? It's basically reading through all these documents, converting them into words, and then trying to figure out what words exist in these documents, and then it creates an inverse list. For each word, what is the frequency of that word being used, and which documents are having that word? That's the list it is maintaining. When you're doing a search, it's basically finding out in this list where that word is, and then basically going to the index which tells us which 4 documents have this word in there. It also has frequency. So it will show you the word which has the, let's say, maximum number of occurrence of that word. It will put that at the top. And I'm saying a very simplistic implementation of the Google search. Then it created more ways to figure out which one of these 4 is more relevant, because it didn't have only 100 documents, it had 100 billion documents. The search queries are not returning 4, but 400,000 results. Now, how does it figure out which one is more valuable than the other? There are other ways of doing it, but let's not go there. Let's say it has these 4. How does it find out which one is more relevant to your interest? It uses a vector space calculation called cosine similarity. Cosine similarity goes by saying that more the frequency of the term being used and inverse document frequency, less number of document on that word, or less number of documents containing that word, higher the likelihood that it is more relevant to you. Does that make sense? Right? If you have 100 documents available to you, only 2 have the words that you are looking for, and one of which has that word 5 times as against the other one only 1 time. There is a likelihood that the one document containing 5 occurrences of this word is more meaningful for you. Right? Let's say you were using 2 words to search, W1, W2. W1 returns that there are 40 documents that has this word. W2 has only 4. Think of it IDF, which is the inverse document frequency. What Google determines, or what this particular cosine similarity principle says, that the word which has lot of occurrence in terms of the frequency of document is probably less relevant because there are too many of them. The one which has less is more relevant, so it's going to give higher weightage to this. Now, how does it calculate that? So that's basically is the cosine similarity, and next slide will explain a little bit more detail. But eventually, what you're doing is this. You've seen this earlier, right? This is a neural network calculation. It figures out the TF-IDF cosine, which is very similar to attention mechanism we talked about, and it calculates the probability, which is doing a cosine calculation of which of these 4 documents should be most probable for you to look at. That's a cosine similarity. It's a dot product, magnitude of vector. At the end of the day, points to remember, it will give you -1 to 1. -1 tells you that the document is irrelevant. 1 tells you that's the one you should be look at it. Still not neural network, right? But very close to that. What it is doing is that it's relying on something called a cosine similarity. That is nothing but a dot product calculation or of a vector product or matrix multiplication that can be used to figure out which one is the most relevant document for your search query. Now, I gave you half the answer. What if you need to convert this to a neural network? What's going to happen here? Come on, guess. How are you going to do whatever else you want to do, healthcare, remote sensing, building a model, I mean, all big things, right? If you can't think of a common, simple problem, which, by the way, was already solved without using neural network. What are we going to do? So, instead of assuming the similarity equation, we're going to use probabilities, right? That's what the neural network is all about, computing probabilities. So what we're going to do, if you look at this one, an argmax function which is actually calculating the possibilities by figuring out the similarity, we're going to replace this with a BERT dot product, which is very similar. I gave you a hint that the attention mechanism is what you're doing, right? So instead of doing the cosine similarity calculation, you let it go through. So 2 changes are happening. One is that this corpse is not using this reverse list which Google was preparing. Instead of this, it is being used for training the network, and then you're using an encoder decoder mechanism like BERT, which is basically performing exact same thing for generation. Rather than searching, you are letting the neural network compute potential solution, and you assign them probability, and then those probability will tell you which one is the more probable answer to your question. Does that make sense? Do you think it will work, or it can work? Who thinks that it's a potentially good solution? Or the other way around, who thinks it is not a good solution? Come on. Something. Today is the least interactive session so far. Listen, there's no right or wrong answer, right? So give me your opinion. What do you think? Will it work or will it not work?
I think it will work.
It will work? Okay. Do you see many of these chatbots being built that way? Why?
I'm not aware of that.
Okay. So actually, let me put it this way. So the three things I asked here. Clearly it will work, right? Because the language models are doing a lot of things. It is generating its creation of the new content, so it will work. Now, the moment you say it will work, there are a couple of different issues. There's an issue that we talked about yesterday, hallucination, for example. In any generation, you do not know if it gives you the wrong answer. I gave you the example where Air Canada was fined by the courts because its chatbot was giving all wrong answers. Even though the answers were there, but it was assigning probability, picking up the wrong answers, right? Third thing, also we talked about yesterday, the cost involved in actually writing a chatbot using neural network is way more higher than doing it the way the Google search is happening right now. So yes, it will work. On two, it will work, but it will have a potential whole lot of risks. Do the risks outweigh the benefits, or the benefits outweigh the risk? The jury is still out. It does answer questions very well. Actually, one of the startups that I work with, we use an LLM-based chatbot to answer a question about the product. 9 out of 10 times it does very well, in the sense that it answers the questions which it does not find in the training data explicitly mentioned. So it does show the latent space and the finding relationship together. 1 out of 10 times it gives the wrong answer. Now, there are guardrails that we have built up, in the sense that rather than giving a wrong answer, except that I do not know this, or say that contact the help desk at this number or at this email, or whatever the case may be. Right? Okay. So let's say that it's doable, it's expensive, it may be a little bit riskier, but potentially a good way of doing things. Are these chatbots a good way of interfacing with neural networks? Yes, no, maybe. And that you should actually have some form of opinion. If you have used ChatGPT, you have interacted it as a chatbot. It works as a chatbot, right? So what are the pros and cons, basically? I have had here a slightly different interpretation, not a ChatGPT in general, but its utilization by either an organization, a company, or maybe a court, maybe a medical system, maybe a legal profession, maybe a tax consultant. I mean, those are some of the use cases. Most of the same problems. I mean, it's fun, it's good for narrow scriptable applications, but the cons is they don't really understand unless you have a huge corpus of information where they start trying to get a feeling that we saw with neural network, where it figured out that the relationship between king and queen is same as men and women, for example, right? Or it figured out is the relationship between India and Delhi is exactly same as in USA and Washington, D.C. No one told it, but it figured it out, right? Expensive, brittle, sometimes they can mirror training data exactly, garbage in, garbage out. Again, all the problems we talked about yesterday, because if you have a chatbot which is becoming an interface for your organization, and if someone who want to sabotage your implementation or want to hurt your branding can train your chatbot to do things that you won't want it to do, right? I mean, if some of you who are doing branding or marketing or those kind of things, right? A lot of brands do not want their brands to be associated with some other things. That could be some other thing, could be a celebrity. If they have in a negative news, those brands don't want their product to be associated with them. So a lot goes in making sure that your branding is working as per your plan. If you leave it to a neural network driven system, somebody else can sabotage, right? All the risks that we talked about yesterday. Okay. So far so good? Okay, let's do a quick look into the implementation of a frame-based system, which was a goal-driven tasks. I'm not going to take too long on this, so I'm going to quickly move on to the second topic that we want to talk about. So generally what you're doing here, this architecture will look like that you have a structure, call it data structure, information structure, which is trying to capture user intention. The user intention is driven by whatever the goal is. So for example, this is what our goal was, this is what the capture of the intention will look like. How do you capture the intention? One of the earliest implementation was done in 1977, which is what I've used it here as an example. I think the reference is there somewhere. What you're trying to do here is that you have set of slots which require to capture user's intention. There's a domain ontology, which is basically saying which words you want user to say for you to recognize, and you're trying to capture those. Slightly different answer, slightly different example here, frame-based dialogue architecture. There's a chatbot which is trying to get user intention and fill that structure that you saw earlier, right? This is just an example. It may ask questions, it may clarify, it may confirm that there is no illogical or invalid answers. There could be some validation associated with the responses that you are providing. Is this model better than the first one? What would you prefer? Let's say you're working for a bank. You're trying to create a conversational agent that, let's say, I don't know whether we do demand draft today or not, but assuming we do demand draft today, let's say it basically wants to have a system that lets you request a demand draft be sent. Or maybe let's say simple, make a bill payment. Let's say you got the electricity bill and you are trying to instruct your bank chatbot to pay the bill, right? Which method is better? This one, frame-based dialogue architecture, or the other one, which were the retrieval-based or generation-based architecture? Which one is better? They could be highly precise because it's a very clearly defined goal. It's a clearly defined requirements, what needs to be there to have that goal. They may also have validation, as I mentioned, when you are providing the answer or gathering the user's intent. The negatives are they can be expensive and slow to create rules because they are very similar to rule-based system or expert system. Somebody needs to define the rule. If the rules change, if the laws change, if the rates change, you need to have a high maintenance there. But they would be more successful, more predictive, less error, less confusing for the users. So, what did we say here? Can someone summarize or have a question before we move on to the next area? Anyone? No questions? Okay. So let me just do a quick 30-second summarization and then see. Keep in mind, you have to learn something to use it in a situation that I have not mentioned here. So what did we do? We looked at the chatbots or conversational agent as one type of application where generative AI might work. And very similar to what we did like in last few days, we looked at historically how exactly they evolved. So they evolved from a Rogerian psychologist-based implementation of asking questions, and we saw a limitation of that. Then we saw that a call tree kind of an implementation where you're asked to provide or pick one out of many choices, and then you follow that. Either you get a success or you end up at a node called frustration because it didn't do what you expected it to do. Then we said that the second type of implementation would be a corpse-based implementation. You could actually organize it in some form of database, or you could do it like the Google is doing. What Google is doing is implementing some kind of similarity algorithm to find out which document has higher probability that you are interested in that as against the other ones. This is, you can implement it as a SQL database, no SQL database, you are querying, you're searching, you're getting the results back. Then finally, we said that you can actually also use the generative AI-driven conversational agents. You're replacing database with learning, and you're replacing the cosine similarity with some kind of a self-attention mechanism or the BERT dot product, and then trying to do an encoder-decoder structure and then get the answer. Then we said that, will it work? The answer was yes, it will work, but it has limitations. It is expensive. People, your opponent can use it to train in ways that you don't want your brand to be acting or doing things. Then we differentiated between a goal-based conversational agent and a generic conversation agent. We said goal-based conversation agent may work better when you have a well-defined structure that you're looking for. If you have all that information, you can actually even validate that before acting on it. Those systems can be highly precise because you know what you're looking for, you can validate it also, etc., but they are expensive to build, expensive to maintain and change. Now, the bottom line is same. We looked at 4 different ways to implement a conversational agent. Depending on what you're trying to do, you pick one or the other, right? Or come up with the 5th one. Okay, anyone has an idea to build a startup? Trying to build a conversational agent for, I don't know, counseling when a new student gets an offer or an admission offer, right? Probably a good use case, build a conversational agent. Yeah? All right. No questions? No ideas? $1 billion startup idea. Okay, all right. So let's move on to the next topic then if there are no questions. Now, I do want definitely for someone to talk about more. So all 4 of you who were doing the GIS, okay? I know what it is, but probably this height doesn't know what the GIS is. So I want one of you to actually explain before we go on to this. What is remote sensing and what is GIS? Who wants to explain? Come on, I got to give you some homework. You gave me homework to prepare this, right? So you have to explain to this side of the team, this side of the class, that what is GIS and what is remote sensing.
Remote sensing is basically sensing features on Earth using some remotely. So using sensors, which for example satellite sensors, you can capture a photograph and use it as digital images and make some operations on it so that we can get some valuable insights on how the features on the Earth behave while interacting with electromagnetic.
All right, this side. Do you understand what is remote sensing imagery is? Okay, so great, thank you. I mean, that was a good introduction. So what we are doing, we're switching gear and trying to look for a new type of application. The one I chose earlier, conversational agent, was something which I presume majority of you were familiar with, had interacted with it, and probably had opinion also about it. Now this is interesting area because it's very specialized. It's pretty close to at least 30, 40 years ago when I was working in this area was like a very esoteric area for two reasons. Okay, before I go to those two reasons, what it is. In a way, it's a photograph. When you take a photograph from your camera, you're actually taking some area. It could be 1%, it could be 10%, it could be, if you're using a zoom lens, you're probably taking an image which is 100 meters away. If you have a more powerful lens, you can probably be shooting 200 meters or 300 meters of imagery. Now, farther you go, more information in your picture. You take a close view of a person, you only see one person, two people, or this class. You move farther. If you remember on day one, we all took pictures. We were like 50 of us, 60 of us. The person kept moving back because everybody needed to fit into the screen. Do these pictures or images interesting? Are they interesting for you? I guess the answer is yes, right? All of you, if you take out your phone, will probably have 5,000 photos on it for multiple reasons, right? So that's your photos and images and cameras, right? Then what happened is that when we started sending satellites in orbits, right? You know all what the satellites are. Yeah? Yes, no, maybe? Has anyone seen a satellite? No? Anyone here? Which one? Where? Go on. You saw the models, not the real one. All of you have seen satellite. You see it every day. Yeah. Moon is a satellite of sun. Right? So what is a satellite? A satellite basically says that it draws its energy from another source. You can see the moon because the sun's light reflects on it. Okay. Now the moon is one satellite. The earth has its own satellites that we send out. Right? What's the difference between moon and the satellites that America has sent or India has sent?
Moon is a natural satellite.
Uh-huh.
And others are man-made.
Okay, that's one difference. There's one more huge difference actually. The man-made satellites that we are sending are called geostationary. Does anyone know what is geostationary and why they are called geostationary?
They seem stationary to Earth because they are
Correct.
the exact.
Correct. The earth is rotating on its axis, earth is rotating around the sun. Geostationary satellites that we send, they are going in the near earth orbit. They're not as far as moon. They're actually a fraction of distance from the actual distance of the moon, but they are placed at an orbit where they look at the same space continuously. So with respect to earth, they seem stationary. They're not. They're moving. Earth is moving, they're moving, but they are stationary relative to each other. Right? So, what do these satellites do? What do these satellites do? Do you use them? Right. Your mobile phones use GPS. The GPS is a functionality provided by these satellites. More than that, initially the satellites were used for communication, telecommunication. If anybody has electronics, you do antenna design, you do communication, right? So they were initially used for communication. That was the first intended use. Then researchers realized, once the camera technology improved, the lenses improved, that if they are looking at the same spot continuously, can we put camera on there? The camera technology has improved big time, but now there are satellites which are not necessarily just the communication satellites, they are remote sensing satellite. Now what is remote sensing? A very powerful camera looking up from, let's say, 200 kilometers high or 50 kilometers high, capturing photographs of the earth and sending it back to us. There's a whole lot of improvement in 30 years when I was working in it. Cameras have become powerful, communication has improved. There were a lot of problems. Earlier camera was very, very poor in terms of resolution, in terms of its power. You know how the cameras work, right? Higher the power, better the pictures you will get, better resolution you will get. Then the problem was that, yes, you've got a lot of data. You got like 10 gig of data. How do you send it? It was not easy to send the information down. You can take a picture, but it takes 2 hours to download. It used to take days to download the data, right? All of these improvements have become now possible. You may have seen newspaper reports where they show movement of enemy forces, the constructions being done, comparison images. This is how Allahabad looks like before Kumbh, this is during Kumbh, this is after Kumbh. You might see those kind of images from the sky, right? You may have seen the pictures of which city is lit up. You go closer to Delhi or Mumbai, and then basically you see that there's a lot more lights out there. So, point I'm trying to make is that remote sensing imagery is just like a photo. It's a photo at higher resolution and higher dimension. Any remote sensing image actually covering some physical space on Earth, right? Now, fast forward today, let's say now you have access to a lot of these imageries. Each of these images has a lot of data. Now you have a problem of interpreting these images, right? Which is a problem what you solved for Facebook when you basically identified your friends. What were you doing? You were identifying a feature. That feature, by the way, happened to be your friend. But when you are interpreting a remote sensing imagery, you're trying to identify, is it a building? Is it a farm? Is it a wheat farm? Is it a sugarcane farm? There are multiple reasons to do that, actually. Let's not go into why we are doing it. But the issue is same. Facebook wanted you to identify who this person is, right? Remote sensing application, I don't know what they call nowadays, but people who are trying to interpret imagery are trying to identify a feature. Is it a road? Is it a river? Is it a ditch? Is it a mountain? Is it a building? Is it a hospital? Whatever the case may be, right? There are a lot of use cases. I mean, I can give you a few of those things basically. Remote sensing imagery was being used in 1988 to make a better estimation of how much wheat is going to be produced, how much rice is going to be produced. We can go into politics and all kinds of things as that people were estimating or not estimating. How many people are, one of the early use cases that we had was that to calculate the amount of deforestation in national parks, right? I mean, if you go by land, visiting them, you make one estimate, but if I'm getting an imagery of a year ago and today, I can visually see them. I can actually extract the features of where the forest cover is still there versus not there, and I can estimate that, okay, we have lost 7% of the forest cover over a period of time. A lot of applications. I mean, I guess today the applications may have changed, but all kinds of things that we were doing, right? As a matter of fact, one interesting project that I was involved with was very, very, I would say, I actually don't know how successful it was. Are there any people who eat fish here or engage with fishery? Fishing is a huge exercise, right? It's part of agriculture. The fish is raised as agriculture. People who are involved in fishing, not the fishing in the river, but in the sea, deep sea fishing. It's a massive operation. There are big ships involved. They actually have massive nets also. If you think about it, the fish in sea especially don't stay in one place. They move. So if you're running a big deep sea fishing business and you go at the wrong place to do fishing one day, you may not find any fish because the fishes are moving. So one of the experiments that we did was, can we use remote sensing imagery to help the deep sea fishermen to locate where the fish are on a given day? And if somebody's interested, we can talk about it later, but I'm just giving you an example of the imagery. Now let's see. Let me ask the people who are doing PhD there. Where do you see the use of generative AI in remote sensing imagery? And the reason I'm saying that I want to understand your perspective, I have just one example that I included today here, but there might be many more.
I'm not sure, but maybe to produce data where similar data where the data loss is there in the image. For example, clouds they disrupt the information capture. So we have blocks where the information cannot happen. Maybe there similar to the neighborhood pixels. Maybe we can generate better user interface.
Okay. All right, let me try to rephrase, and we want to stop in about 15-20 minutes for the break, and then we'll continue a little later. So very similar. The use case that I picked up is very similar. Now, I'll mention one more thing before we go here. The area which is being helped in remote sensing imagery interpretation is very similar to what you would normally do in image processing. If anybody has done a subject of image processing or a course in image processing, you would know that, right? All kinds of mathematics obviously there, a lot of filters, a lot of feature enhancements, feature identification, right? So one of the use case that we can think about, and that's the one I'm taking the example of, again, a published work, not my work, obviously. So you can actually look into this. Maybe you guys are familiar with it, those who are doing a research on it. Think of a situation where you have access to these remote sensing imagery, very similar to what Facebook was doing 10 years ago, trying to identify your friends in a photograph. Here you're trying to identify MNNIT guest house from a remote sensing imagery. Can you do that, right? So if you're trying to follow the Gen AI, right, go back to what I talked about on day 2 and day 3. You're building an AI-based system. What are the steps? The very first thing that you need is to train the system that you want to do. To train the system, supervised learning, you need to have data where you can train it to say that this is what a building looks like. This is what a housing complex looks like. This is what, whatever, a train line looks like. This is how a road looks like, etc., etc. One of the problem that is being looked at, it was always there. I mean, it was a manual exercise. It was an exercise earlier trying to do use the image processing techniques to make the image look better. There are all kinds of mathematics involved because really speaking, these images are not two-dimensional. There's a parallax. There's really an overlap of images. You want to sometimes join these images. I'm leaving out all of that thing. So let's say you're trying to build a generative AI which can help you interpret an image, a remote sensing image. The first step, you need to train it. Can you use Gen AI to generate the synthetic training data? Because unless you can train, the Gen AI cannot help you with interpretation. Make sense? So let's look at it. If we are trying to build a system that can help us generate data for training a large language model. So a little bit of a circle here. We are using the large language model to generate the training data, which will be used to train another large language model to actually use the real remote sensing imagery and predict or identify or extract features from it. Make sense? All right, let's look at a few of these things. So a typical sample is going to look like these are black and white images. These are images which look really bad, and you're trying to identify what is in this image. A typical remote sensing expert would be looking at these images, trying to make sense of it, trying to get the meaningful, actionable intelligence out of those things, right? So our goal here is to say, can we use these artificial sample and train so that it can be used to identify natural geographic phenomena or even man-made structures for that matter, right? That's the goal. Does it sound familiar or something similar? So what we are trying to do is something like this. You may start with this kind of image or this kind of image, and then you can try to identify what's in there. It may be a bridge, a forest, a stadium, an industrial complex, parking lot, shopping center, whatever the case may be. Basically, you're doing exactly the same thing as I mentioned earlier already twice, that you are identifying a friend and putting a label on it. You're identifying a feature here and assigning it a label, right? As simple as that. Right? How would you go about doing it? I mean, I'm asking this question, but the answer should be very familiar by now, because it doesn't matter what problem you're trying to solve using AI, all or most of the solutions look very similar. Supervised learning, training data, build a mechanism to do unsupervised, and then search, which includes generating labels and assign probability, pick one. I mean, there are a lot of details behind it, but in general, it'll look like exactly same, right? So, if you think about it, what is it going to do? It's a classic machine learning problem if you think about it. Because you're giving it data, you're assigning labels as your supervised learning, and then giving it more data to say, can you use your learning to identify this? But it's not trivial, because it's not trivial for words and sentences. It's even more non-trivial for something like an image, which is not very clear. So, a lot of things where the samples could be imbalanced. Now, this is again a very similar thing in what we talked about, the TF-IDF similarity. Think of it this way. The feature that you are most interested in is the feature is most rare. Because if the feature is everywhere, then you're not interested in it. If I am, let's say, the Defense Ministry of India, I'm interested in finding out where is the nuclear power plant for whatever country I'm, let's say, interested in. I'm not interested in where the houses are or where the shopping centers are. I'm interested in where the other strategically, militarily related point, right? So the thing that you are most interested in is the thing hardest to find. If it is hardest to find, how do you even train your network? Because if you can't even find it, you can't use the label for it. Now one might say that, okay, just train it with any other label. That defeats the purpose, because it will then find the right things and say that this is what you're looking for. So one of the ways you can do is use the synthetic data. Use the generative AI to generate the data that is very similar to the real rare occurrence of a feature that you are interested in, and use that for learning. So same way, what I'm saying is that frequently occurring classes is not an issue, because that can easily be done. All neural networks are greedy. Remember, I've used this term greedy a lot of time. You are trying to figure out the best thing to do for a rarely occurring object, because that's the goal. Okay? Specific example, finding it complicated, and very few such objects exist, so we have a problem there. What are we going to do? Okay, so two things here I'm going to do. This is a problem which is normally used by, have you guys used, or any of you who are doing the PhD in remote sensing or GIS, any sample databases for images that you have used to train whatever? Yes? No? Which one? Which one? Okay, all right. So I was a little afraid that if I'm going to give you an example that you're already familiar with, you're not getting anything new. So this is the research which was published, I think, last year. Okay, I don't have the year here. So it's using another publicly available data set. So obviously, I'm giving you a new example so you can start using it and try to figure it out. So it's using that database. So here's an example from this. It is called AID, a benchmark data set for aerial scene classification. Have you seen this one? Okay, have a look at it. So what it has is that I think thousands of images, I don't know the exact number, a couple of thousand images where each of these things are defined. What a forest looks like, what a baseball field looks like, what a beach looks like, all kinds of, what a railway station looks like, because you're going to use these images to train your model and then give it an image which is unlabeled and then say, can it identify features, right? The question is that how do you go about it? The basic solution is exactly same, right? You get the data, you label it, have the learning process run as a supervised learning, make sure that your model learns the right thing, and then start experimenting by giving it unseen pictures. There's one more thing we talked about. Don't use all your training data for training. Don't use all your training data for learning. You keep it for validation also. Remember the step I used called regularization. You don't want your model to learn exact thing. You want them to generalize. So that if you've seen one beach, you should be able to identify a beach which looks same but not exactly same, similar. Right? You want model to generalize. Everything that we talked about day 4, 5, 6, etc., they're all same things, right? So what this is doing actually, this work, it's using these benchmark data set and a process called diffusion. Have you heard of diffusion? Denoising or creating more crisper data sets. Now that is also, the advantage there is that there's a library which actually is available in public domain that you can use. So you can use this benchmark data set, you can use the library to generate more imagery to train your model if you wish to. So what it is doing is that diffusion model training on all available classes. Classes means the class of imagery that is showing you to learn one type of feature, and then use it to generate more data, right? Now keep in mind, I mentioned that synthetic data is a problem because synthetic data may actually reduce the learning, but in the cases like this when we do not have the data, this is one way of doing it. Can someone remember an example? I think 2 days ago we talked about where the same kind of approach, was it? Yeah, day before yesterday when we were looking at benefits. Come on. If you're looking for a job in Gen AI, how are you going to do it? There was specifically an example very similar to this. Healthcare, brain imagery, for example, or any kind of data. You need synthetic data to train your Gen AI or your model so that it can be used for the other purposes, but we don't have that many of scans, right? It's a health data, it's a public, it's a private data, it's a secrecy issue involved. So you need to generate those kind of samples to actually train them, okay? So right now I'll show you an example of what was produced. This was a training data for identifying mountains. So this was generated applying diffusion model. So the goal here, what I'm describing here is that not to use the Gen AI for actually feature identification, but use a specific model to generate more synthetic data to train the Gen AI. The way it works is actually you're finding out noise in images. So you start with an image, find out the noise, filter the noise out, build the feature that you're interested in more sharp, more easily identifiable. Okay? The way you do it is that you run the same process over and over again, create distortions, and then use it to have some kind of a GAN, which basically tells you, is it desirable, is it not desirable, have a feedback mechanism, which basically says that, is the noise helping you get better image, or it's getting more of a distortion than in the wrong direction. So really what you're doing is that you're introducing the noise and hoping to get that noise which is to generate a clear or a clean image. Have you ever seen an example where a service comes along and says, do you have a picture or a photograph of your grandparents, for example? A fuzzy black and white picture that may have lost colors, that may have lost even the shades of blacks. Right? There are services which are actually taking that picture and cleaning it up and give you a colored view of your grandparents or like some very old picture, right? All of it is happening based on very similar technology, right? So what we are doing is that we are saying that we are introducing noise not to obfuscate but actually enhance the image so that it can help us do the feature generation. So let me show you an example how this specific model worked. So you started with the dense imagery like this, which is actually an area which has a lot of housing. You run the multiple iteration of this particular diffusion probabilistic model, and there's a reference for the paper that I'm describing, and that's where all the imageries come from. And then iteratively get to the point where these features becoming more and more better. Now, this is not a typical image processing or a remote sensing mechanism thing, because the idea in the remote sensing was to go the other way, remove noise, which is what you would do if you are manually working on it, in the sense that if you are really working on one image and trying to get better. What we are trying to do is the other way around. We are introducing noise but the goal is to not obfuscate a feature, but iteratively make it better so that it does look like what we were looking for. And then use that synthetic data to train the model, which can then be used to identify features of interest. Make sense? Yes. Okay, so that's a good question. Anyone can answer? Do you have an idea? How does introducing the noise help?
So in diffusion models, the noise is being added, and the model tries to reduce the noise again to get the original image. It is a way to train a model in a better way to get the original data or the extracted data.
Or better data, yes. So the noise is a known term that's being used. I could have used a perturbation as a term as well. So the noise is just being, so think of it this way. You have a fuzzy data. That is not the exact data that you're looking for, right? One way to say that I know what modification or perturbation I need to do to get to the real data. If you know that, you can do it. Lot of existing image processing or remote sensing image processing goes on that logic, that I will remove this, I will make this change here. Here, you don't know which is the right way. You are introducing a perturbation. Same thing like a feedback, and then you figure out, did it make it better? Did it make it worse? If it make it worse, go in the opposite direction. So you are introducing the noise in order to get better outcome. That's what you're doing, which is what a diffusion model usually does. Okay, anybody else or any questions? This is not just limited to the diffusion model and not just limited for image processing. If anybody is in financial domain, the stock price movement is based on diffusion model. Brownian motion, I don't know if anybody has heard of it. I asked this question earlier also. Not Brownian motion, but the pricing of a derivative, which is also based on diffusion model actually. I mean, if you think about it, almost every phenomena in the world is probably using a very few basic fundamental mathematical techniques, or you can model the real world using those basic mathematical techniques. Okay, one last opportunity. One more question before we take the break, if there is any. Yes, no, maybe? No. Okay. All right. So why don't we take a break here and let's meet at 20 minutes, 11:50, right? And when we come back, we're going to talk about the last topic for the day. If you're trying to build a language model, how exactly you're going to go about it. Okay? All right, guys. Let's just take a break here then.